Yeah, I mean, it's better if you can share the screen.
You know what I mean?
Recording has begun.
So everything is like that?
Yes,
I
you
just
just
said
put
it
in
is
your.
okay, they can see it that way. Let's just move on. There's 4 people on Zoom.
Okay.
So we have most of the people here.
Okay.
Okay. So just
I'm sorry. This
No
is
worries, this shouldn't have been said like do not have, I mean, guests are not, it's used to, so, issue.
okay. So I'll just present here. That's okay.
Why are they scanning this?
this is already happening.
Oh, for attendance? Okay. That's my first time.
I know, right? Is that crazy? Wait, why did they want to know how many people show up or something?
No,
Would you like me to
we have to
introduce-
register this.
Introduce you based on what we have here.
Sure, you don't have to read all of it. I mean, it doesn't.
It's not a lot.
It's up to you. Whatever you want to do. Sorry. Wait, how big is the seminar? There's so many students. But if they don't do it, then you won't know.
They should hear us, right? I unmuted. So how about you with this one?
Yeah.
You need to have it as close as possible.
Mm-hmm. It's what?
It's not very strong.
That's okay. I don't need to shout.
No.
How's that? Does that seem like it's okay? I have no idea. Is that on? This is a little
Yeah, you could. I don't know how. But it's
No, I know, but I don't have like a belt or
so you could.
You want me to use that?
What do you? Hello.
That one word.
So there's no I'm wearing a dress. There's no It's very awkward. Yeah, I will. It's okay. Just leave it here.
Yeah, I'm teaching this class.
How's that? Can people, I mean, I don't feel like it's, there's no, you know what I mean?
Okay. Let's go as is. That's not good.
Is that okay? Do you hear anything? I don't think it's actually working. But then again, I could be wrong. Oh, okay, very close.
You need it close, yeah.
How about like here? How about here?
Yeah.
That's better?
Can you hear?
Can the people in the back hear me? Nothing. It's very like faint. I just want to know, so I know. Hey, the students in the back, can you hear me? Okay, they're good.
Shall we start? You got everybody here? Got some folks online. Okay. Sounds good. Let's start. Hello, everybody. Today's ECE seminar. I'm Samira Mibagher, and I'm honored to introduce Dr. Lisa Wu-Wales.
from Duke University today. Lisa is an assistant professor of computer science and ECE at Duke University. Prior to Duke, she was a postdoctoral researcher at the UC Berkeley and research scientist at Intel Labs. Her research interests include computer architecture, microarchitecture, hardware acceleration, hardware-software co-design, emerging application in big data, healthcare, and artificial intelligence. Dr. Wills has a PhD in computer science from Columbia University. Her research is recognized with multiple awards such as NSA Career Award, VMware Early Career Faculty Grant, IEEE Micro Topics 3 times, and 2 times honorable mention of Micro and Best Paper Award from Micro and ISPAS. Please join me welcoming Dr. Wills.
Good morning. My name is Lisa, and thank you for the kind introduction. So I'm going to talk about 3 recent projects that I'm doing with my students at Duke. And the theme is to broaden the field of heterogeneous computing. So let's see. So I have a lab at Duke called Apex, and I'm not a very formal speaker, so please interrupt me at any time if you have questions. And if we don't finish the 3 projects, that's fine. If there's something that you're more interested in, I'm happy to talk to you after, or you can send me email because I'm very close. It's a 30-minute drive, you know, and on Zoom it always works. Okay, so I'm going to first tell you about the research themes and goals that I have. And we're in this post-Moore's law era that hardware specialization is basically one of the most promising solutions to obtain more efficiency. And to that end, there are 2 main themes in my research that contribute to this broadening the field of heterogeneous computing. So the first theme is to make hardware design as intuitive and accessible as software development. And under this theme, I'm going to talk about 2 projects. The first one is this AI-assisted synthesis predictor that basically allow us to perform design space exploration in a very expedited way. And another project is a accelerator composer we kind of call Beethoven. And this is kind of unpublished work, so I won't spend a ton of time on it, but I'm hoping it's going to get in this year. So, and then we can start having tutorials for people to use this tool because I think it's very useful. And this composer basically provides a programming abstraction that's for highly productive development of accelerators. And the second theme is basically to leverage these accelerated systems once you design them to actually address some real-world challenges and hopefully deliver some meaningful impact. And in this theme, I'm going to highlight a protein discovery engine called PROS. And so these research goals, they all work synergistically together, and you're going to see throughout my talk today. Okay. So the first project I'm going to highlight, of course, my PhD students are the ones who are awesome and did all the work. So you're going to see their pictures throughout the project. And actually, Entropy just graduated in December of 2024. And he's my first graduated PhD student, so I'm really proud of him. And he is going to be a postdoc at Hong Kong Technology of Science and University of Technology and Science, sorry. And then he's going to go on the academia market, so I'm very proud of him. So, okay, so the first project, we name it SNS. So SNS actually stands for SNS is not a synthesizer. And this SNS leverages deep learning to expedite the accelerated development. So the main motivation for using deep learning to expedite this is that synthesis is slow. So let's look at one example. Let's say we have an idea for an accelerator, and we want to figure out the best design for the workloads that we care about, okay? So we start with a base design. Let's say a 32 by 32 systolic array, right? Everyone's using systolic array, TPU is using systolic array. So let's start with that. And let's say we wanted to support very conventional, 32-bit floating point data types, okay? And then we wanted to just do like a simple multiply accumulates for the PEs, okay? So let's run synthesis and see what the timing, power, and area would be, okay? So unfortunately, it takes about 1 whole day to run the synthesis for this very simple design on traditional synthesis tool chains like Synopsys, design compiler, and ICC even for place and route. So what if we wanted to see the implication of supporting a different data type? Well, run more synthesis. And then what about exploring different systolic array sizes? Run more synthesis. What about augmenting the PE logic itself? Well, run more synthesis. So because the traditional synthesis toolchain is so slow, in fact, it makes doing any reasonable design space exploration using estimated physical characteristics nearly impossible, okay, such as using performance per watt, or if you want to use performance per area as your design or optimization targets, you have to run synthesis like crazy, and it takes so long. So with the embedded systems nowadays also have like tens and hundreds of accelerators, having synthesis predictions that run fast and accurate is actually really crucial, okay? So our approach is to use a deep learning-based method to quickly predict an arbitrary hardware design's physical characteristics. What I mean by that is predict its timing, predict so how fast can it run, predict the power, and predict the area, okay? So we use this graph intermediate representation, we call graph IR, to represent the design, okay? We then extract these circuit paths from the circuit graph using a modified transformer model we call circuit former, okay, to predict these path characteristics. And then we finally use a multi-level perceptron to aggregate the circuit path information to obtain the attributes of the entire design, okay? So today's talk is going to offer a more detailed look at the approach, but there will be details that I have to omit for time constraint, but more details are in the paper. So you're welcome to read it and then send me questions when you have them. This work is published at ISCA 2022, and there's a version 2, which I won't even get to talk about, is published at Micro 2023. Okay, so here is a hardware description language example of how SNS works. So the first step is we're gonna get a graph IR representation of the hardware design, okay? So here's an example of just a multiply accumulate unit, right, a MAC. And here's the Verilog version of it, okay? So you put it into the graph IR generator. Then what it comes out is we use YOSYS, the open source HDL compiler, to parse and compile the input design source code to the circuit representation, which includes all the basic functional blocks, which are the nodes, okay? And then the wiring connections, which are basically the circuit graph of the design. So the MAC is gonna look like you have 2 I/O ports, you have a 16-bit multiplier, you have a 16-bit adder, and then you have this D flip-flop. Okay, basically the register, 16-bit register that saves the accumulation results. Then you have this output, C, okay? Questions so far about the graph IR? It's good? Yes.
Are you just using this?
Yes.
You probably have a custom that's highly, optimized, and then use that as a building block for physical design. You wouldn't synthesize that.
So for when you say customized MAC, what do you mean by that? Like you mean like the circuit itself?
Yeah, like that would be your cell, and that would be a building. That would be a standard cell.
Right.
And you'd have a 16-bit one, and maybe have multiple of those.
Yep.
That your VLSI designers would already have pre-built.
Yep.
I know that's intensive, and there's trade-offs.
Yep.
I don't know that you would synthesize. Would we want to synthesize this part or synthesize the systolic array using them as standard cells?
Yep. So I think for the tool, it's supposed to give you an estimation of what happens. But if you have optimizations that's custom, right, then it's gonna be different. However, what the tool does is it will provide you with a design space, okay? So let's say if, excuse me, if your whole entire design space uses this particular custom Mac, that's okay, because it's showing you the relative differences between different designs. So, you know, having 4 versus A, you know, or having a bigger grid versus smaller grid. Does that kind of make sense? So it has, it almost like, it doesn't care about what you ultimately do because it's an estimator. And what it does, it just allows you to pick the best designs. And then you can go and do your traditional, you know, hand design, whatever. But at least you don't have to sift through like 1,000 designs to figure out which ones might be the Pareto optimal. So that's like kind of the goal. Awesome. So this is a very simple example though, to your point. Okay, so from the graph IR, what happens is we want to sample actually paths in this design. And obviously in this particular example, the paths are super simple. Okay, so I'm just giving you examples so you know how the tool works in sampling these paths. So only paths beginning and ending with an input port or a register or a D flip-flop are sampled. We're basically trying to make it so the path essentially captures what's a one-cycle behavior, okay? So we kind of restrict what kind of paths you can sample, okay? So because we can estimate what the one-cycle behavior would be, then we can easily estimate what the timing, area, and power of the entire design, okay? So here are 4 examples of the paths that I might sample. One of them would be from the input output to the multiply to the add and then to the register, okay? Another one, another one, another one, okay? So it's not necessary to actually sample all the paths of a hardware design because lots of the paths are actually similar. And you don't need, if you sample all of them, it's not gonna give you additional information, especially for the model, okay? So in the paper, we use a DFS-based sampling algorithm, and there's like parameters you can tune to sample more or less paths, depending on how accurate you want your estimation to be, okay? And you can read more about that in the paper. So once we have these sample circuit paths, then we want to use a predictor to actually predict some physical characteristics, okay? And the simplest and the most intuitive one is let's just use linear regression, okay? And you can take account of each type of vertices on the circuit path as inputs because longer circuit paths will have more vertices, right? Which means each path will have more functional units, right? And more vertices will lead to larger area, larger power, and also longer cycle time, right? That's pretty intuitive. But a linear regression model is unable to infer based on the order or the placement of the vertices in a circuit path. Okay, so let's look at an example. If there is a path that contains like a 16-bit adder followed by a 16-bit multiplier, the synthesis toolchain is going to synthesize this into 2 separate modules, right? An add followed by a multiply, okay? And if there is a path that contains a 16-bit multiplier and a 16-bit adder, the synthesis toolchain is actually going to optimize this and say, this is a MAC, right? We can do something different. It's not going to be 2 modules. I'm going to have a MAC as 1 unit, okay? But if you use a linear regression model, these 2 to the linear regressor looks exactly the same because it's just 1 adder and 1 multiplier. It does not care about the order of where, you know, these units actually sit. So you're going to produce estimated exact same area, power, and timing, which is not right, right? So in order to capture the order and the placement of the functional units on the circuit path, we need to choose a more sophisticated predictor than a linear regressor. So how do we do this? We are going to use an NLP model, okay? So many NLP models are designed to learn the ordering, the placement, and also relationship between the words, okay? Making them good candidates. So the circuit former is essentially an extremely trimmed down version of an NLP model. So we don't use words or subwords as tokens, right, to predict sentence, but we use like these functional units plus the width of the bus as the vocabulary, okay? And then we predict what the sentence, which now is a circuit path characteristic, would be. And transformers actually use attention heads to extract these relationships from one functional unit to another in a circuit path. So rather than trying to understand each functional unit independently. So our circuit former is able to use each node in a circuit graph as a token, and then the circuit path as a sentence to predict these physical characteristics of a design, such as like area, power, and timing. So not just from individual functional units, but actually a complete circuit path that has all the nodes along these lines while we're learning the node adjacency, the ordering, and frequency information. Okay? Questions about that? Okay. I can't tell, like there's like blank stares. So okay, I'll keep going. You just let me know if you're lost. Okay, so one insight of using the path-based approach as opposed to a graph-based or a GNN-based approach, which a lot of prior works did, is that the path lengths of hardware designs actually don't vary that much, okay, between small and large designs. And so the path-based approach allows us to actually provide scalability of predicting large arbitrary designs. So GNN-based models consume too much memory or encounter like significant slowdowns when you predict large designs because they propose to ingest the whole entire design into one graph, okay? And another advantage of using the path-based approach is that it's much more efficient and less time consuming if I have to generate a database to train my model. Because every time when you're synthesizing something, you're only synthesizing one circuit path at a time. You don't do the whole entire design. And then what we do is, at the end of the day, we aggregate them together using an MLP, okay? So lastly, the predictor scales well quickly to produce inferences for hardware designs up to like 18 million gates. And the prior designs can only do about 50 to 100,000 gates. So we were able to scale up a lot because it's much easier to do path-based prediction as opposed to graph-based. Let's see. I feel like I skipped the MLP part for some reason, but let me just say it. So after the circuit former, there is a multi-level perceptron. What it does is it aggregates all the path level characteristics into the whole design characteristics. So for example, you would use like a max function if you're looking for cycle time, right? Because the slowest path is going to determine your frequency. And if you're looking for area or power, you use a sum aggregation, right? And then you kind of figure out, with that and the sample rate, you can figure out approximately what the area would be. So these are just estimates, right? So it doesn't have to be accurate enough for you to tape out a chip, okay? Because we're not saying use this to replace your traditional, synthesis toolchain at all, not at all, okay? So let me see, there's more. Oh, okay, so here I talk about the SIGGAN. So another novelty of the approach comes from the insight that paths are actually sequences, okay? And there are a lot of other modeling tools out there for like NLP. And one of them is what's called a GAN, which stands for Generative Adversarial Network for Sequences, and so, or SIGGAN. So we actually use SIGGAN model to learn and also generate new, unique, and complete circuit paths that are similar to the paths that's sampled. Because there are not a lot of open source hardware out there for us to actually be able to build up enough data to train the model to a certain accuracy, we have to rely on this, basically generating our own path that's realistic and be able to train the model. So we use that SIGGAN to combat the data scarcity, okay? Which is kind of like an important point because we just haven't gotten to the point where people are open sourcing hardware that much. And obviously, the more we build up infrastructure, the more people will be willing to share data, right? And having extracted, okay, so this is the part that I was kind of jumping ahead of myself. We basically use the perceptron to aggregate these characteristics into the power, area, and timing of the entire design. Okay, so since I already talked, yes?
So if you sample the same path twice, do you get meaning is there any statistical variability that you see in your data?
Yeah, so for the, when we use the DFS, that actually allows us to sample, let's say, from a parent to like 3 arbitrary children paths or something like that. So of course, there will be times where you sample the same paths, but that probably just means that representatively in your circuit, you have a lot of paths that's similar. Does that make sense?
Yeah, but like even if you sampled exactly the same path, do you see any change in the readings that you observe? Is there any kind of noise or anything like that that makes the readings different?
When you say readings, can you expand on what you mean?
So like the timing that you get, the 0.4, the 0.4.
Oh, the database? The database is generated actually by my student going in and then synthesizing that path. The ground truth is built upon the synthesis tool results, synopsis, actually.
If you pass it through the neural net, does it give you the same answer for the same inputs? Is that what you're saying?
So the neural, yeah, so like I guess so, but I mean I'm wondering if there's any kind of deterministic in terms of what you get as an output, or is there, I mean, because these are circuits, and I presume that there might be some noise somewhere in a circuit?
No, because the data sets are generated by synthesizing each path, right? So there's no non-determinism, right? Because then you build up this database, and then you feed it into the model to train it. So the prediction is going to come out the same every time. It's the same as training any other model. We're not trying to change anything on the fly or, you know, with signal noise, and it's not that sophisticated. Does that answer your question? Okay, cool. So my students actually like spend time and went in and generate all the designs, you know, so we do have a database of these things, right? So then we can train the model. But other people are, and the tool is actually open source, and anyone can go take the model and then add more training data, right, to make it more accurate if they wanted to. Okay. But those are really good questions. I have not had those before, so I'm happy that you're asking me. Okay, so now I'm gonna show some results, the prediction results. Here, we perform an experiment where we train and evaluate a predictor using a training set size of 50%, okay? And then we use the other 50 as the testing set. So we will do like a twofold cross validation where it's the data set is split into parts A and B. So you train on part A and then evaluate it using part B, or train on part B and evaluate it using part A. So the y-axis here will plot the predictive physical characteristic, while the x-axis is going to plot the synthesis results produced by the synopsis design compiler, okay? And the closer the predictions are to the diagonal line of y equals x, that means the better predictions that is, okay? And we report the mean absolute error percentage here. It looks like it's a lot of error, but it's like way better than prior work. I think it's just a difficult thing to do, just in general, okay? And here I'm showing the speed up of the predictor compared to the synopsis design compiler. So the y-axis plots the runtime of our model, SNS, and the x-axis plots the runtime of synopsis design compiler. So the runtimes are measured in wall clock time, and it's run on a dual socket 48-core Xeon Gold server. And each design point is represented as a circle. And the area and the complexity of the design is actually proportional to how big the size is of the circle. Okay, so bigger circle, more complex design. Okay, And on average, the speed up, our predictor runs about 760 times faster. And you can see that the larger the design, the more speed up actually we can obtain, okay? I think it's because it just takes so long to synthesize a large design, and that's why. It's not because our predictor is doing anything different from larger designs. And the largest design we have experimented with contains 18 million gates, and it's actually a large 16-core accelerator for computing 2D stencils, which is the green circle up there. So this design's physical characteristics are predicted in around 20 seconds when you run our predictor. But if you run like Synopsys DC for this particular design, it took around like 2.5 hours, okay? So I'm gonna quickly show one case study that we did. So one of the strengths of SNS is basically the speed, and then also like the natural use case is basically to enable this large design space exploration, okay? So it doesn't have to be accelerators, right? It can be like any design that you want, okay? So we chose to use a reasonably complex general purpose core, which is the Berkeley RISC-V out of order core, or they call it BOOM, okay? So we use BOOM to perform a DSE, right? And you all know how to design an accelerator, a processor, I'm assuming. And so we can vary the parameters, such as like, let's say branch predictor type, I want the core width to be different, you know, number of memory ports, instruction fetch width, you know, ROB size, physical integer register file size, issue slots, L1 data cache ways, you know, associativity, right? And then we searched through around 2,600 designs, and we want to find out what's the Pareto designs for a BOOM core, okay, using all these different parameters. So we went through about 2,600 designs, and here is the results. So we generated all the sort of the area and the power numbers and the timing, which is frequency, right, based on SNS. And we plot the performance on the y-axis, area and power on the x-axis, and we select a best performing design, okay, here. And then a most power efficient design, which is, you know, perf area, most area efficient design and the most power efficient design. So it would have taken around like 45 days to run this, okay? Instead, it took SNS about 2 hours, okay? So you can imagine if you have a ton of parameters you want to experiment with, using SNS is a really low-cost way of doing that.
Every one of these design points then, so you ran all of these designs through synthesis? Okay.
Yeah, isn't that crazy?
Did it predict the right one?
I think actually we did not, no, I'm sorry. We did not run these. We did not run these for 45 days, if that's what you're asking. But we do analyze the designs in the paper, and yes, they make sense. They make sense according to what, like, the core mark score and all that. But we did do a smaller experiment to do exactly what you said, which was we wanted to know if the designs picked by SNS was the same, you know, like as if you were to do the whole thing, and yes, it was. Even though the relative, you know, like the absolute is different, right, but the relative is exactly the same.
For a sample set of...
Yeah. Okay. I think maybe he did like 100 or something like that, but just nothing like too crazy. But yeah, because we had the same question, right? It's like, is this just spitting out junk, or is this actually like, you know, reliable, right? So yeah, it's accurate. I mean, to the purpose that it's supposed to do, I guess, is what I should say. Okay, so I think that's the end of the SNS, and I'm just gonna skip over this significance because I already talked about it. Scalability, okay, because path-based, and then we can generate more samples. Yes?
Yeah, I've also got a question regarding SNS.
Yes.
Because you said SNS, the key is to have this cycle behavior in your...
Yes.
Right? You know, in that case, when you circuit informer and the MLP to predict power or area,
yep,
how would between different paths? Because when you do placement, for example, there are some paths you cannot do,
Yes,
predicting
I
of the
understand.
paths,
Yes.
right?
So the placement and routing is not predicted by SNS at all, because we have not trained the model to do that. So, but that's obviously a concern about the prediction, right? Because this is only the ground truth that's trained only is by design compiler. So that also doesn't have any of that information. But you're right. And the second version, we actually fixed some of these inaccuracies, meaning that sometimes you have paths that actually, with the gates, how it's laid out, they cancel each other, okay? But in the SNS V1, we did not take that into account. So we had trained a new model in V2. What it does is actually use contrastive learning, and it says, hey, these circuits are different, so put them as far apart as possible. These circuits are equivalent, put them as close as possible. And with that way of training, the accuracy went up by a lot, okay? So I think there are always things that you're correcting, and I feel like the next thing, if I get a student who wants to do this, will be doing place and route, because that's gonna have a completely different, challenge than we have already encountered. But I will say it's surprising even to me that the V2, just using this contrastive learning, and also we kind of fine-tuned how we train the model into like this pre-trained phase and then this domain adaptation phase, okay, where we train specifically for certain technology. We were able to like train on one technology and then predict on other technologies, which was like a surprise to me. And the fine-tuning takes very short amount of time. Like once you have sort of like the base. And the only time it doesn't do well is if you have some like fundamental change in the standard cell. Like for example, if you go from like 90 to 45, it's too hard to predict because your 90 standard cell is so much different than 45. But if you did like, I think we did 45, 28 to 16 is pretty like okay. Like, so it depends on like what technology and what's underneath it. But using a better way of training the model actually makes a huge difference. So this is just the first version, and we learned some things from it, but the second version is better, but you may not need the second version if you don't care about, if you say, hey, this one is trained on 45 nanometer and I'm good with this, then you can use this. But the second version is better. Okay. So yes.
See that the timing of the design is not being met, your time is not being met, and you want to maybe use better standard sets like faster or per year standard sets. Is that being accounted by the synthesis? Those optimizations for synthesis?
So some parts of the optimization is encountered, but not from the technology perspective. However, what is good about SNS is when it predicts timing for you, it tells you where the path is coming from. So what that actually allows you to do is instead of having to figure out where your critical path is or something that doesn't meet timing, it tells you, it'll say, here's a path that gives me the prediction of your whole design because it's the slowest one. And it lists out all the functional units for you. So you actually can use that as sort of like a debugging aid, where you say, everything else is actually running fine, but this path sticks out. So go look at it. But it definitely does not take into like, switching technological cells, nothing like that, right? Because it's just a model. It's just a ML model, right? It doesn't do that.
How many paths do you have to? I don't really know how SNS works exactly. Do you sample a bunch of paths?
Yep, from a design.
So you take the design.
Yep.
You sample a bunch of paths.
Yep.
You run each of those paths through your machine learning.
Yep.
Right, and you a bunch of paths.
Yep.
Sample, for example, for the boom core.
Uh,
And how do you know
how do you know that's enough? Well, because the model is already trained, meaning like we have already tuned it, and we tell you all the parameters in the paper, and so the model as it is considered to be good enough, and then the error rates are reported and stuff. But if you wanted something better, you could give it more training data.
So as part of the training, how many paths you need to sample for a given size design?
Yeah.
Okay.
And there are some parameters you can tune, but from what I can recall, in a couple years, you don't need a ton of them. Because a lot of paths are actually very similar. Like even if their functions are different, but the functional units that you're using, like, you know, are not that different. Because like it's just a lot of combinational logic, right? There's nothing like that was like really crazy. Yes.
So you're training that data is not publicly available data as actual training model from something?
Yes, we have the data. We don't know how to make it public because it's like terabytes of data. And I'm sorry? Yeah, we have them. They're generated by like hours and hours of Synopsys DC. Because that's the ground truth. We basically take the open source design and we synthesize them. We synthesize the paths, we synthesize the whole entire design.
Existing open source design.
No, the paths are from, yes. Well, the paths are coming from just running through any open source design through ECE. Right? So then we can like, yeah, you got it. And then we also generate synthetic paths using the seq-GAN. Yeah? But we do have the data set that we use. It's just that like we don't know how to make it public because it's like terabytes of data unless, you know, Duke is willing to host like a FTP server of some sort. So, but we do have the model available. You can just download the model. And then you can add more data to train it if you want. The model is completely open source with the weights and everything, right?
So do you have a sense that the most critical will have other parts that look similar to it? Because if not, then it seems that a priori guarantee that you would have sampled such a path, right?
Yes, they're pretty much uniformly distributed, the different types of paths that we sample. And you can up the sampling size and see that it doesn't produce any different results. And that's how you know.
So, but in that case, if they're completely uniformly distributed and there is no sort of variability, then it would suffice to just sample just a few number of parts.
Yeah, but depends on the design. So I think that's why we have that parameter that you can tune. But for the designs we looked at, right, we chose a set of parameters that suffices. Okay. So I think I only have what, 15 minutes? Okay, so I'll get to this one quickly, and then I might like talk about pros for like 2 slides because I don't have time. Okay, so this is the one that's we're still working on, but it's pretty much done. We just need to start giving tutorials on this. It's an accelerator composer we call Beethoven, and it provides this platform-agnostic programming abstraction to compose accelerated systems. Okay, so before I talk about Beethoven, let's look at the hardware design landscape today. So the y-axis is going to plot the performance from low to high, and then the x-axis is going to plot the development effort from low to high to develop an accelerator, let's just say, okay? So this horizontal line is going to represent a hardware design's maximum achievable performance, okay? So high-level synthesis is going to take an algorithm in C or C++, right? And it's going to compile it into an RTL design, okay? But HLS requires expert knowledge to achieve optimum results, and the software to hardware translation sometimes introduce these performance area and power overhead that are difficult to diagnose and optimize away. But there are definitely designs that's very regular, and HLS does excellent, okay? But writing, another way of designing hardware is what? Write the hardware description language by hand, okay? It takes more effort, it's unintuitive, error-prone, and also difficult to debug, even though it can reach the maximum performance, and presumably that's why you do that, okay? So what we want to do is have our cake and eat it too, basically. So we're proposing this multi-core hardware software accelerated design framework that's just going to provide a flexible and reusable SoC integration environment through the separation of concerns. So basically, we're going to allow the accelerator programmers to do their thing, and then we're going to allow the platform developers an easier way of developing and generating the platform-specific type of system blocks. And we're hoping to exploit this productivity sweet spot at the knee of the curve, okay, where you don't spend too much time, but you get like good enough performance that you're satisfied. But we're not saying like Beethoven is going to give you like the maximum performance, okay, because that's like too big a claim, okay. So at the lowest level of Beethoven hierarchy, we're going to have this custom functional unit that the developer actually will implement, okay? They'll implement this, we call this an accelerator core, okay? So here's a core. So the core actually comes with these abstractions that we provide to talk to memory, reader and writer, and also like a low-code scratchpad type of, and then it comes with a command interface that we provide, okay? So all the cores that you can instantiate, however many, okay, Beethoven will instantiate them for you if you just tell Beethoven how many you want. And multiple cores will form what we call a system, okay? So in one accelerator, you might want to have different types of accelerator cores, so then you'll have different systems, okay? And then for the systems, the Beethoven basically generates all these system components that's in white. The only thing the accelerator developer has to worry about is the accelerator core in purple. Okay, so that's the whole point of this, this framework, is so that Beethoven can help you do these tasks that you have to do over and over, okay? And there's no point for someone to keep doing it. We just automate it, okay? And what it does is it actually allows the accelerator to communicate with the host, and they communicate through this command subsystem using ROC instruction format. ROC is a RISC-V ISA extension. And the reason we do that is because then Beethoven designs can basically integrate with any RISC-V systems that supports this ROC interface, okay? And then the commands are actually sent over the MMIO interface. And to support more complex programs, Beethoven also allows the accelerator cores to communicate between each other, okay?
Questions, either way.
Oh, 30 more minutes. Yes. Oh, okay. Okay, good. But you guys are asking me questions, right? So we don't need question like time later, right? If someone's holding the questions, just ask them. So I know how to like pace my talk. Okay. So the orange arrows here will show how the accelerator communicates with the memory subsystem. And within a Beethoven core, right, as I have pointed out already, there's like the reader, the writer, and the scratch pad. So the reader writers are communicating to external memory controller, routing through a tile link protocol. Okay. So what Beethoven does, it will route all these memory channels hierarchically, automatically. So the accelerator designers don't have to do that. Okay. All right. So I'm just showing a very simple case study, and then I'll show a more complicated case study. The very simple one is the mem copy, okay? We basically do them in 4 different flavors. One is we use like a handwritten HDL version of the mem copy. The other one, and then we use Beethoven with or without TLP. Okay, let me explain TLP. TLP stands for transactional level parallelism, and basically it just says use multiple axis ID or not. Okay, because for communicating to memory, for something that's very naive, you don't need to use multiple axis IDs. You can just use one axis ID. Okay. So the use of the different IDs will allow the controller to actually return data out of order. And let me show you here. Let me just highlight this performance. Basically, it's showing that Beethoven with or without TLP performs can achieve about the same as what handwritten HDL will give you in terms of utilizing memory bandwidth. Okay, and HLS, for some reason, do not use multiple axis IDs, and it really hurts them. And somebody can go in and change it, but then you might as well just write your own HDL at that point, okay? But that's just, we're doing this use case not to show HLS is terrible. It's just to show you that it's complex, and it's not to say Beethoven is so great. All it's saying is, even for very simple things like memcopy, okay, it's difficult to design it to maximize the memory bandwidth, okay? So these are some of the annotated timing diagram to show you exactly what's going on. So the first one shows the HLS. So if you can see, these are the read request, the read data, and then there's the write data, write request. And then the requests are complete in order because they have single transaction IDs. And they use them, reuse them over and over, okay? So for Beethoven, there are actually multiple transaction IDs, and they can return out of order if they wanted to. And then in handwritten RTL, they can actually use 64 beats per request. So that makes it very efficient, okay? So actually completes faster than what Beethoven can do. But we also tried Beethoven of 64 beats, and I didn't show it here, but basically performs the same as HLS, okay? So performs the same as HDL, handwritten HDL. So HLS, for some reason, it doesn't matter if you specify 16 beats per request or 64 beats per request, it always defaults to 16 beats. And my students spend so much time trying to parameterize it, give it different things, it just doesn't work, okay, for this instance. So I feel like HLS, maybe in some instances, these things happen. So then you can't really optimize it, even when you want to, okay? So then there's this case study of a attention accelerator that's published, I think in maybe Micro or ISCA, I can't remember. So we try to use it as a complicated case study where we say, you know what, instead of having a memcopy as our accelerator core, yes.
Before you move on to this.
Yes.
For the memcopy.
Yes.
So what language are you expressing the design in? I mean, HLS takes it in as C. So
yep.
Okay, so this is all C, either Beethoven or HLS.
No, so Beethoven takes Chisel or Verilog.
Okay.
And then the handwritten HDL is in Chisel.
Okay. And what about
C. And with lots of pragmas.
Okay.
You may have mentioned this. How do you handle out of order hazards?
Oh, for Beethoven, yeah. It's under the hood. So my students actually, he has a specific way of making sure that we have some way of tracking when they're coming back. So these are actually, we cannot get into the memory controller ourselves, okay? But the multiple axis IDs are supported by the memory controller. So these are measured actually by putting in a little performance monitoring block right before, right at the boundary to see what happens. So we don't handle it ourselves. It's the memory controller that actually handles it. So you can either take advantage of it or not, depending on what it is. So with handwritten HDL, obviously you can, right? You can take advantage of it. And for Beethoven, he kind of programmed something in there that can allow it to use multiple AXI-IDs, and that's about it. There's like nothing special that he had to do, really, because the memory controller takes care of it. Because we're not trying to like reinvent a memory controller or anything like that. All we're trying to do is try to utilize the system blocks that was given to us as much as possible. You're still thinking. Do you have a question?
I am. I'm trying to figure out. It helped to see the C code for the.
Yes, it's in the paper. Oh, wait, sorry. Paper is not published. Not yet. Otherwise, I'll just tell you to read it. When it's.
No, I'm not reviewing it. Anyway.
Wait, when it's published, I'll send you a copy.
Yeah, sure. I guess what I'm asking is, what is being optimized here? It has the ability to sort of say, write something, and the timing is absolutely not specified, right? The cycles are not specified, and HLS will put flip-flops at places it wants to off, IP cycle time, and you see what I'm saying?
Yeah.
And is that what's going on here? Like, the mem copy is literally just this array, and it's of a certain size, and then let HLS have at it.
Yep.
And you'll see what it, where it puts
Yep.
stuff.
Yep.
Okay.
There's no, we don't like doctor anything, but we try to optimize it by like using different pragmas, But in this case, we don't, right?
It shows a starting point. This array being copied into that array.
Yes.
Fair enough.
So this is a more complicated case study, okay? And it's an attention accelerator, basically showing you if you have a really complicated accelerator core, Beethoven can also handle it. And by the way, it'll do a better job, placing and routing it for you on the FPGA than other tools may be, okay? So in here, the attention accelerator basically has 3 stages, and I don't really want to like talk about what the attention accelerator does, but all you need to know is it's a 3-stage pipelined accelerator. So here you can see the I/O, okay, and then there's the reader and the writer, which is the query reader and inference writer, and then the scratch pads that's managed by your accelerator. So these are the interfaces we provide to the developer. Basically, it's reader, writer, scratch pad. And scratch pad read or scratch pad write. And all the routings between the cores and such is all done by the Beethoven, and so is the host and memory communication to the accelerator. It also generates like a control program for you, so you can specify like, I want the accelerator to have these 3 instructions. And we provide like a C wrapper for you by generating them, and then you can tell the accelerator what to do, okay? So we measure the performance of this on CPU, GPU, and then with Beethoven-generated accelerator, okay? So I don't think they actually take advantage of the task level parallelism as much as Beethoven, the CPU and GPU implementations, okay? Because we were able to instantiate 23 cores on a F1 instance in the cloud. And here is what the layout looks like. So another thing that Beethoven is good at is it actually is SLR aware, okay? So it can route multi-die FPGAs efficiently. And there is also little heuristics in there that allows you to figure out, where the core should go. And if they communicate with each other, don't put them too far away, because once you cross the SLR boundary, you kind of increase timing, okay? So all that is under the hood, so the developers don't have to worry about it. Because what we really want to do is just make it as easy as possible so that people can start, just designing their accelerator without worrying about all these nitty-gritty things that's very necessary, okay, in order to deliver the performance that you want. So we were able to place like 23 cores, and these are the shells that come with the AWS F1s, which is like memory controllers and such, like DMAs and whatever. And we were able to get 96% utilization, which is like really difficult to achieve. So that's why the performance is so good. Yes?
Regarding this EQ accelerator. So for this workload, is that compute-bound problem?
Good question. So both. Both. So there are different things that you do because they have to read in a lot of data. That's why we had the scratch pads here, to make it so that it's not as memory bound. But everything else is compute bound, like dot product and exponent and, you know.
I see. That's why I'm wondering why the GPU has such low throughput. It's weird because on GPU, the peak bandwidth is high, the memory bandwidth is high, and also the compute throughput is high. So, but you showed, if I remember correctly, you showed something like ops per second.
Yeah.
It's very low.
Yeah.
In terms of utilization of.
Yep.
That's why I'm wondering, what makes this
so
bad?
So non-linear function like exponent, it doesn't work well. Okay. And also in the A3 paper, which is so the accelerator design actually came from the A3 paper that was done by someone else. Okay. It was from like Seoul National University. Okay. So we basically took their design. Okay, so in their paper, they explain why they designed it this way. Like, we didn't come up with our own design. We kind of took their design and said, hey, can task-level parallelism help in this problem? Because you have so many attention heads, you can do them all in parallel. There's no reason why you couldn't. Okay, and so they also compared the GPU. And I think it's because it's complex, and then you have some local reuse, but not all the time. And then you also have, like, nonlinear functions you have to support, right? So I think it makes it difficult to get high throughput. Okay, do I have time?
Another around 15 minutes.
Okay, great. So I'm going to talk about PROS quickly. So PROS stands for protein systolic engine. Okay, so it's actually basically an accelerator for BERT model. Okay, if you're not familiar with BERT, is a natural language processing model that's old now. Okay, because now LLM is taking over the world. But BERT's structure is a transformer model, which is also the basic structure of LLM. So you could say, some of these techniques that we explore here can be applied. So let me talk about why I want to do protein discovery, because we kind of talk about, okay, so there's like the broadening the field of heterogeneous computing, and then the second theme was, can we use this to apply to some real world problems? And this is one of them, okay? So the goal of protein discovery is actually to find permutations of these antibody proteins that can bind a bad protein to stop the growth of the cancer cells. So for example, the HER2 protein for breast cancer. So pharmaceutical companies are actually spending $80 billion a year, is that crazy, to develop new drugs with a lab to market average timeline of 12 years. And a 90% failure rate in human trials. And discovering these drugs that target specific proteins is very expensive and time consuming. And predicting these side effects that make drug toxic are even more difficult to predict. So the confluence of the recent innovation in deep learning algorithms and also the large amount of data on protein interactions we already collected, right, from the drugs that we've already developed, and the advancements in like this computational power will allow us to finally be able to predict what we're interested in, which is protein-protein interactions, okay? And we want to predict them more accurately than like wet lab experiments or even traditional computational biology, algorithms will allow. So we want to be able to improve the quality of drug candidates that go through human trials. So let me speak a little bit about like ML model and like its role in something like this. So ML model obviously cannot give you a drug that works, right? But what it can do is nowadays for drug discovery, people basically is like throwing darts at the wall, right? And it's like, what sticks, But the problem is like the search space is so large, what you could do is use NLP to help you to narrow the space, narrow, to give you good candidates. Then this way you say, these 10 are really promising. Go and do your development for the next 2 years or whatever. Instead of saying like throwing the darts at the wall for like 12 years later, you finally find something. So that's the whole point of like a NLP model. It's not to say, hey, this is gonna give you a drug you need. It's just that it's saying, these are the ones you might wanna look at. They're pretty good. Okay, because I just don't want anyone to misconstrue like what the model is doing, right? Just in general, okay. So then let's look at how we can leverage NLP for protein discovery. So we start by looking at a ubiquitous NLP model, which is the bird-style transformer model. And the input sequence of language tokens are sent through a pre-trained bird model. And then a downstream task is fine-tuned to train and predict the translation or natural language understanding, question answering, whatever downstream task you want, okay? So then for proteins, they're actually just a chain of amino acids, right? So we can use one letter to represent each of the amino acid and then pre-train a protein bird model on proteins across the tree of life, right? And then downstream tasks such as like protein structure, prediction, binding affinity, stability, et cetera, can then be fine-tuned and then predicted with good accuracy. So the Google AlphaFold actually used the augmentation of a transformer model to predict the protein structures, the 3D structures. And we don't do that here. We actually focus on binding affinity to tell us if an antibody protein can bind well to a bad protein and is a good drug candidate. So what are some of the challenges to run Protein Bird on existing platform? Why can't we just run it on GPU or CPU, right? So first, the existing CNN, DNN accelerators are not efficient or performant when you want to do these bird-style models. The second is that few accelerators that do accelerate them only accelerate one part of it, like attention, for example, okay? And then the third is that GPU and TPU systems are very efficient at executing deep learning models inferences. They are optimized for short input token lengths. What I mean is when you do a search, okay, the input token length is around 80 tokens, okay? So let me show you this graph. So so traditional language model, when you're doing a search to rank, your search results, the token lengths for inputs are usually 30 to 80 tokens, okay? And then with TPU and GPU support, maybe like 256 or 512 input tokens. So the majority of the proteins in the human bodies are actually somewhere between 300 to like 3,000 amino acids, okay? And here I'm plotting scaled inference runtime versus input sequence length on A100. So when the input length actually increases, the runtime increases quadratically, okay? And we propose this accelerator pros that's actually going to accelerate the bulk of the transformer inference runtime, and it targets for longer input lengths, okay? And this is actually the results that we got. I'm just showing you right now to show you like why it's important for us to accelerate it. Because if it's already doing so well here, why do we need to care, right, about getting it more efficient? And the reason is because proteins are longer, and also, with like large language models, the input token lengths are actually increasing, right? Now they want to do maybe like thousands or more, right? Because you're feeding in documents as opposed to just like a search query, okay? Okay, so here's a figure that shows the power efficiency measured in the number of inferences per second per watt. So on the y-axis. And then the input sequence lengths on the x-axis. So we plot the measured power efficiency on A100, TPU V2, and TPU V3, okay? So they show similar efficiency, actually, at short input lengths, if you look at them. But A100 has a clear advantage when the input sequences length increases. And I'm going to show this graph again later and plot pros on it for you. So in order to architect and microarchitect an accelerator for a protein bird, the first step is to characterize the application. Okay, what is actually run? Why is it slow, right? We want to know that. So we observe that actually, as input sequence length increase, the matrix multiply to SIMD operation ratio changes. Okay, so these are like element-wise SIMD here, right? And as you increase the input sequence length, the ratio changes where the element-wise SIMD becomes more dominant, okay? And we also noticed that matrix multiplies performed in BERT are actually on much larger matrices than the batch matrix multiplies. So the size difference will also inform some of our design decisions later, okay? Questions so far? Okay, so we perform a deeper characterization of the application and found that actually 90% of the total inference time is spent in 3 different data flows, just 3, okay, no more. So I'm gonna use different symbols to represent the data flows and show you. I'm gonna use this for MAML, I'm gonna use this for SIMD, I'm gonna use this for special functions, so like GALU, okay? So the first sequence is basically just a MAML followed by a dependent matrix SIMD operation, such as matrix add, for example, okay? And the second one is basically the same, but repeated twice, and then followed by a special function. The third one is basically a MAML followed by a dependent matrix divide, and then followed by exponential. That's it. These 3 data flows comprises across the layers of what the transformer inference is, okay? So if we can just optimize for these 3 data flows, we're done. Okay, so we call this sort of like a coarse-grained computational patterns, okay? And then that way we can also optimize across model layers instead of looking at 1 layer at a time, okay? So in addition, besides what I just told you, it turns out that these sequences actually map to matrix sizes large, medium, and small, okay? So we chose to design PROS to be actually a heterogeneous systolic array, each with different sizes and functionality, okay? So that's basically what PROS is. Let me not keep going. Do you guys have questions about PROS? Should I like get to the conclusion? Because, yes? Okay, let me just, so one thing is PROS is output stationary. So it allows streaming inputs, so that way we don't run out of memory. But that comes with a trade-off, because that means the bandwidth to feed the data has to be very high, okay? So that's one sort of trade-off that we're willing to make, except nowadays, the highest bandwidth communication between an accelerator and a host is probably like NVLink. So we propose using NVLink with this particular accelerator. Because like TPUs are way stationary, okay? So they don't need this much communication bandwidth. Okay, let me skip to the end. And here is what the final result is that PROS is able to deliver much more power efficiency than GPU and TPU. And here is the result on speed up versus like different interconnect. And you can see that if you don't use NVLink 2.0 or 3.0, then PROS doesn't make sense. It will not perform as expected. So I think this is it. So my last slide. So I have some ongoing projects, and I welcome questions about that. I'm currently trying to tape out a PROS proof of concept with my students in 16 nanometer. And we want to use GPT-NEO as a demonstration that it can run that. And another student in my lab is working on accelerating diffusion models. And another one is working on TFHE, which is homomorphic encryption. And then we're also looking into VectorDB recently. And also we're trying to open source a lot of infrastructure that we built up, because I believe that that will help the community as a whole, right? And people can actually do their research much more expediently as opposed to developing everything, in-house, every student that comes in, because it just wastes a lot of time. So we're doing this systolic array simulator that allows you to customize whatever you want to do and give you performance estimates. And if we integrate that with SNS, then you can get, maybe some physical characteristics. That's the end. Thank you for your attention. Let me know if you have more questions. Go ahead.
Yeah, so for the third part of your talk, you mentioned that the computational bottlenecks in existing methods main data flows, right? And they involve large matrix multiplication. I was wondering, is there some special matrices that you exploit to sparse, maybe they are flow rank, and these are that you sort of exploit.
I'm taking this off. Can you say the last part again? Because I didn't hear you.
So, I mean, like, I was curious, how do you sort of bring down the complexity of these matrix multiplications? Is there some special structure to these matrices? Maybe they're sparse, a lot of the entries are zero, or they're flow rank structure. Is that something that you exploit, or is there some other way of?
We don't exploit the different structures, but we do. It's a solid array is actually very efficient at matrix multiply, so there is no reason to. The only thing we're doing different is that we're saying using homogeneous systolic arrays is not as efficient if you have heterogeneous ones. Another thing I didn't show here is
the advantage over a TPU.
yes,
Also is systolic.
yes. So actually, in the paper, we compare step by step to how TPU executes one layer of the model, and it's a little bit like. They have a very efficient way of doing it. They have a global buffer that they use to sort of make sure that they have enough data to feed, that they're running at a certain throughput. But we didn't want that because we wanted more like the heterogeneity, and we also want like the streaming nature. What that allows us to do is actually having like a multi-threaded control program for the accelerator where we say, do this, do this, do this. And then put more threads together, you can actually hide the dependencies between what you need to do between different types of systolic array. Because you know how the data flows, it uses different types of systolic arrays. So what you really want to do is you want to say, I'm going to schedule M here, and then E here, and G here for different sort of iterations of what you're computing. So that way, we can get like 80 or 90% utilization on these systolic arrays versus TPU probably normally gets like somewhere between 20 to 50%.
From the insights of optimizing and designing an array and scheduling things better, did you get some insights so you could optimize the TPU flow, or is it just it's too limited?
It's different.
Okay.
It's very different, right? And they do a lot of optimizations that we don't do.
Okay.
Because you know what I mean. So it's. But I will say though, the students do the systolic array simulator. They like dug into TPU, validate the model with what the TPU is doing, even with like not a lot of public knowledge. And they were able to get like an error rate below 5% or some crazy thing. That's why we want to open source it. You know, people don't have this as a comparison. They always have to run TPU and have no idea what's going on. So the more we understand, the more we can get something better, right? But I think they're just fundamentally pros and TPU are just very different. Also, TPU doesn't target like long input. Now the V5 does. I don't know, but we haven't looked into that yet. So.
That's what he cares about.
You have a question?